Hi, I'm Nick. I'll be going through the Introduction to Containers at MSI workshop today, which is an interactive, can follow along with the commands I'm running, carpentries style workshop. Go ahead and paste a link to the material that I'll be going over today in chat. So if you'd like to follow along there, you have that option. This is also good for reviewing after the fact. The material on that site has the descriptive text and then examples going through each of the major topics that we're going to be talking about today. So it's an excellent tool for reviewing things afterwards if you are inclined to do so. Today's workshop is also being recorded and will be posted to the MSI YouTube page. Not quite sure what the turnaround time on that is, but I think that it is usually within a couple of weeks of the tutorial being given under the current workflow. Just doing a couple of things here for admin on backend and set myself a timer so that we can take a break about halfway through the material. So first, before we get started on how to use this Apptainer tool, I think it's useful to motivate why we might want such a thing and sort of describe what a container solution in general is. Apptainer is one of several pieces of software that we would describe as a container solution that allows you to sort of package up software and distribute it in our case as a single file or as some small number of files to other people, to other centers where folks can run that package that you sent to them without having to do anything aside from have the container software itself installed. This is appealing for researchers like ourselves because we might have fairly complex software workflows that require installing a bunch of things that could conflict with each other or could be really finicky to all get installed in the same environment. And we also collaborate with folks running on different resources. We might move to other computational resources through the course of our career. And it's really nice to be able to take the workflow that you developed and hand off the software required for that to a collaborator, to your future self, to folks reviewing a paper in certain cases. And containers can allow us to have access to some of those options where if we were installing bare metal, that would be a little tricky. So to sort of explore why that is, I'm going to share and talk through a couple of graphics here. There's the window I want. All right. So if you are joining us from the software installation at MSI workshop that I gave a couple of weeks ago, we're going to be sort of discussing the difference between installing via a containerized solution versus installing in a more standard way. I can call this direct installation or installing via bare metal, which is what we primarily focused on in that tutorial. And so that bare metal or standard direct installation is what we are illustrating here, where we imagine that we own a workstation or a laptop, and we are able to swap out any of the hardware that we need to. We can buy a new graphics card, we can upgrade the storage, we can get more RAM if someone is willing to sell it to us, which is always a challenge these days. We can select what operating system and what version of that operating system we want to have installed and running on that hardware. We could even multi-boot if we want to have multiple operating systems available to us there. So we are really not pinned down on what we're installing to. We can install whatever dependencies we want, either using the operating system's built-in tools for doing so, or installing them manually. Again, as we explored last time in that software management workshop. And then finally, on top of all of that, we can install the piece of software that we actually want to use to perform our research. And we can install as many of those pieces of software as we like, sort of fiddling with the various parts of the workstation that we own in order to meet whatever installation requirements that this particular software package has. Now, this is a fine way to do things. This is how software is most often deployed when you're installing like Microsoft Office to your laptop. This is sort of what you are interacting with most likely, is some flavor of this. But it can be a little tricky for software that has like really complex dependencies or doesn't run on an operating system that you want to use. And we can also run into issues when two pieces of this target software that we want have conflicting requirements. Like they both run fine on a workstation that you could assemble, but one of them requires a different operating system or a fundamentally different set of dependencies. And then there are some questions about how we get those to play nicely together on the same system. And there are ways to do that, and we explored them in that software management tutorial. But we don't have to necessarily engage with those issues. And in fact, on multi-user resources like the cluster that MSI provides, we're not really able to fully engage with tweaking all of these knobs to get our different target software installed. So on the cluster, we have a more restricted set of options as users for what we can change, what we can sort of tweak in order to get our target software installed. We have no control over the hardware, really. That's whatever MSI has purchased and will purchase. And we can participate in whatever process to try and steer that decision. But it's really whatever hardware is in the basement down in B40 of Walter is what we have available to us. We also don't have much influence, if any, over the operating system. That's whatever flavor of Linux and version of that flavor that the sysadmins are currently providing for us, due to whatever combination of security and stability requirements that they are needing to hit. Then we have a little more control over the dependencies that we install. There are some that come along with the operating system, and there will be some that will be incompatible with the operating system that is being provided. So saying this is sysadmin influence because we're sort of restricted a little bit in what we can do here, and also where we can install things. So we don't have administrative access to write to system directories, which can be inconvenient for installing some packages under some circumstances. So we can sort of use workarounds in this space to try and get the dependencies we need installed in order to finally, on top of all of that, install the target software that we want. And really navigating this in particular, getting around the restrictions on a sysadmin influenced level of the system is what our software management workshop was last time. So this is the environment that we are working in. And as I said, well, we can work around this. It's not always super convenient to do so. And so we can consider approaches that allow us to sort of get into an environment that is a little more independent of sysadmin control so that we can install what we need to install and get along to our research. Our next image here sort of illustrating two of these approaches and highlighting the difference between them. So there are sort of two broad categories of approach to encapsulating the environment you need to run a particular piece of software. And these would be the virtual machine approach, illustrated over here with these green bubbles, and then the container approach is what we'll be going into more detail today on. It isn't so important to know the details of how virtual machines specifically work, but it's important to know perhaps that containers are not virtual machines, and so can't quite do everything that a virtual machine can do, and also we don't have quite as many responsibilities as we would if we were to run a virtual machine. And the way a virtual machine works in broad strokes is you have sort of these individual encapsulated environments where you have your one or more pieces of software that you want to actually use for your work, the dependencies that are required for it, and then a guest operating system that is fully encapsulated inside of this virtual machine concept. And you can have several of these virtual machines side by side serving different needs, providing different software, providing different operating systems. And then these interface with the underlying hardware via a piece of software known as a hypervisor that allows the kernels from the guest operating systems here to interact with the hardware. It mediates that communication. And this is an approach that has a lot of success in enterprise environments for deploying software at scale, although containers continue to gain popularity there. It's not super popular at multi-user centers like MSI because there are some security and stability concerns about having this hypervisor mediated direct communication between the operating system and the hardware that make it a little less friendly to contend with in an environment like MSI. So what we provide instead is a workflow or breakdown rather that looks a little bit more like this, where we have these different container encapsulations that have the target software, the set of dependencies we need to run that software, and we don't have to provide a fully configured guest operating system for that. There is no kernel inside of a container. Then these containers communicate with a container engine, which is running as part of the host operating system. And then the host operating system mediates communication with the hardware. And this ends up being a much nicer approach for providing a secure and stable multi-user environment. And it also frees us from having to do a lot of very low-level operating system configuration stuff, as we might have to do with some of these virtual machine type approaches. Now, in terms of the container solutions that will be mentioned today, the main one that we're going to be using is called Apptainer, which is a fork of Singularity, which is they're basically functionally the same. I don't think they've started to diverge in feature set yet, to the best of my knowledge. But they are the Singularity project was originally sort of the container project that was designed from the ground up to run in a multi-user cluster environment and to be suitable for use in academic research. And then AppTainer branched away from that for licensing and intellectual property reasons. And we follow the AppTainer branch of that particular project for some of those same intellectual property and licensing reasons. But if you see a workflow that says that it's compatible with Singularity or requires Singularity, at least as of time of presentation here, it is almost guaranteed that you will be able to use AppTainer to run that same workflow, just swapping out some of the commands, AppTainer for Singularity, and swapping out some of the names of the environment variables, usually just, again, swapping AppTainer for Singularity in the name of those variables. Though you'll want to check the documentation to be sure, because those could diverge at any time in principle. You may have also heard of Docker as another container solution that has some popularity. That is arguably the most popular container solution currently, although that landscape continues to change. And we don't provide Docker at MSI for similar reasons as to why we don't provide VMs. It wasn't quite designed to run in a secure and stable manner on a shared user resource. So we can't directly run Docker commands, but luckily AppTainer does allow us to run Docker containers after translating them from their Docker format to their Singularity format. So we still have access to that whole large library of containers that folks have built up in the Docker infrastructure. And we'll look at how to utilize those a little bit as we move ahead. Oh, and then one bit of vocabulary that's important to know as well before we get into our examples here. I'll be talking about two related concepts a lot, a container versus an image. And when we're looking at the examples here, and we're talking about running one of these pieces of software, a container is the particular running instance of a set of software and whatever dependencies. If it's not currently running, then the container doesn't really exist. And we can talk about the containers as these temporary things that start and then go away. Whereas the file that contains all of the information here that gets spun up into a container is known as an image file. And that is the permanent thing that exists on disk that we can send around to other folks and they can use it to run their own containers. I sometimes get the two terms twisted a little bit. I'm going to try to be good and keep them correctly split for our work today, but know that the image file is intended to be that permanent file that you use to instantiate one or more containers, which are these ephemeral running pieces of software that go away when they close. Do folks have questions about our introductory material before we continue? And feel free to post questions in the chat there. I have that open and I can see them. And we have a small group today, so if you'd also like to come on microphone and ask the question verbally, that would also be fine. Seeing and hearing none, we'll go ahead and move along with the material. Get my terminal shared here. thing out of the way of my typing. All right. Is the text a good size on screen for folks to read? All right, thumbs up. Thank you. All righty. So in order to use Aptainer, we need access to the Aptainer command. To get access to the Aptainer command, we can load the Aptainer module here. I am already logged in to Agate here on one of the login nodes. So if you'd like to follow along, find yourself a terminal on one of the Agate login nodes, and we'll be able to proceed alongside. So I'll say module load Aptainer, and now I have access to the Aptainer command. And we can check what version of Aptainer we're running. Looks like it's currently 1.4.5-3, which I believe is relatively recent. Should be. Maintenance day was yesterday, so this we had the opportunity to update it then. We can also, as is standard for a lot of command line tools, use --help to see what is available to us for the Aptainer command. And we can see a lot of available subcommands. We're only going to be exploring a relatively restricted subset of these today. But know that there is additional functionality here that we are not going to discuss that you can look into in the official Aptainer documentation, which is relatively approachable for looking at the interfaces for these different subcommands. One of the ways that we will frequently use Aptainer or any container solution is we will want to download an image file from somewhere else in order to run containers from that image file. Whether this is because there's some container that other researchers have made available that you'd like to grab, or you want to grab some container to customize to your own needs, or if you are grabbing a container that you've already customized and you've uploaded to one of these repositories. And so the downloading and running is a very common workflow. And to do this, one of the things that we need to think about is the image registry, which is where you are currently searching for image files when you use the subset of commands that look for those remote images. And we can add ourselves a remote repository, say Aptainer remote add, and there's no login for this. We'll say -- no login. Call this Scilabs cloud, and then we'll say clouds.scicloud.io. And this gives us access to the repository that Scilabs provides of Singularity/Aptainer images once we run this. I think this is going to throw an error for me because I already have this as a remote, but if you don't already have this set up, you should see a confirmation message that the Scilabs cloud was added. It would be info instead of fatal. And we can say remote list to look at the different remotes that we have. There's my Scilabs cloud there. I've got the Aptainer cloud as well, which is our default remote. And then I have this MSI registry, which is something that I use in the course of my software management work, but that is not currently user accessible. So you'll probably see these two if you've just added Scilab's Cloud alongside it. Now, if we want to switch which remote we're using, we can say remote use, and then we give the name of the remote repository that we'd like to have active. And then if we say list, doesn't change anything because I already had it set as default. All right. Well, we got our info confirming that Scilab's Cloud is now in use. Just around curiosity. Okay. Okay. So our little default check moves back and forth depending on which one we have currently set up. So that's how you can tell which one is currently active for using, for instance, the apptainer search command. So I'm going to run then again the apptainer remote use Scilab's Cloud so that I'm back in line with my workshop material here, so I don't get unexpected behavior. And then we will use the search command to search the Scilab's Cloud repository to see what is available that matches a particular string. So say apptainer search Rocky Linux, where this is an operating system. It's actually the same flavor that we run at MSI. We run Rocky 8. Rocky 9 and 10 are also available for use depending on what containers we are interested in running. This will take just a moment to run through and give us some results here. And sometimes, depending on server load, it's fairly quick today. Sometimes this will time out and not return anything at all. In that case, you can always go to the Scilab's Cloud website in a browser. I pasted the link in chat there, and explore what is available that way. Their search functionality on that website is not so much more advanced than the R-string search here, but it's at least more responsive on average. So we can see that we have a number of images compatible with our platform that match Rocky Linux here. And if we want to grab one of these, we'll say we want to grab 8.6 here. I can say pull library : / I'm reproducing the URI here. So library : / library / default / Rocky Linux 8. You can see after the colon here we have in this case, 2 comma separated items. If we were looking at the one above, we don't have any commas here, so we only have one tag is what this part of the URI is known as. Whereas here we have 2 tags, and we have 3 tags to choose from if we were to be grabbing a Rocky Linux 9, for example. If you don't provide a tag, then you default, I believe, to whatever is listed first here. But I prefer, where possible, to include the explicit tag that I want, so I know exactly what I'm downloading in case that default behavior changes. I can always look back and know what command I ran to get what tag at what time. Let's go ahead and run that pull command. It's going to download a library image. It's not especially large, so it's going to download fairly quickly for us here. And then we have a new file here, this Rocky Linux 8.sif. where .cif stands for Singularity Image File. So even Aptainer is still using this .cif format. And then now that we have this stored locally, we could choose to use this to run software inside of a Rocky Linux 8 environment. Now we're also able to, as I mentioned, pull from Docker compatible resources. So I'll demonstrate that for the first time here, where if you identify the image that you want from Docker Hub, I'll go ahead and link the Docker Hub in the chat as well. You can craft a URI to download from Docker. Aptainer pull. Our URI will start with Docker for Docker Hub, // and then be the name of the project, and then the tag that you want to get. Sometimes you'll have the name of the group / the name of the project, as we had like library and default, or at Docker Hub, you can just have the name of the project for certain things. And if we go ahead and run that, so there's still a downloading step. Then we have this creating CIF file step with some warnings. And this is the step where Aptainer is converting from the Docker format to the Aptainer format. And now if we ls, we have our Rocky Linux 9.cif file present here for us to use if we are so inclined. So now that we have these, let's try running some stuff inside them. First, though, let's run outside. We'll ls-f /. So this is just to demonstrate what we get when we list the contents of the root directory of the file system on our host here on the aggit login node. Then I'm also going to run the id command to demonstrate the results of that on our sort of host context here, where my username and current primary group are both listed at the beginning of this, and then a list of the other groups that I am a member of. Your list may not be quite so long depending on your particular research workflows. And these will both change a little bit when we are inside of our container that we start from our image file. So if we want to just run an interactive shell inside, let's say, Rocky Linux 8, I can say Aptainer shell is our new subcommand. And then Rocky Linux 8.cif, so we give Aptainer shell the name of the image file that we want to run inside of. Excuse me, and then we are dropped into a different shell prompt here, where it says singularity and gives me a caret, and I can start typing to interact inside of this context. So if I ls-f the root file system here, you see that I get a different result, and it's formatted differently compared to in the host context. Notably, there are some MSI-specific things like scratch.global common that are not present currently inside of our container. Projects is also missing, perhaps very notably, depending on what kind of data you're trying to ingest. And if I run ID, I get a slightly different result as well. I still have the same user identity inside of the container context here. I'm still my MSI username. I'm still a member of my primary group. And my primary group is still one of the groups that I'm a member of. But the rest of these groups have been lost inside of the container context. So that's something to keep in mind when you are using data from multiple different groups. Um, making sure that you have the permissions on the directories containing that data and on the data itself set appropriately so that whatever the primary group you want to run inside your container as is able to access them. Otherwise, you can get into some sort of permissions issue edge cases where MSI staff can't access the stuff that's present in the Rosetta group, for instance. I'm not sure if that's true, but that could cause a problem depending on how permissions are set up for whatever Rosetta data exists. Then if we want to exit this context and drop back into the host, we can either hit Control D to drop out of the shell, or we can type exit to achieve the same result. And now we are back to the excuse me, back to the shell prompt on our login node. Now, I'm pointing out the different directories that are visible versus not visible inside and out. I will immediately provide you the remedy for that if you have data that lives in, say, global Scratch that needs to be processed, or equivalently in a project directory or any other location that does not exist inside of the container. We can say apptainer shell again, but this time we're going to add -- bind as an option. And then we'll say I want to bind scratch.global. And we could leave it just like this, and this would bind in the scratch.global directory as the scratch.global directory inside the container. So it would look the same in both cases. I could also give it a new name, call it my scratch. So I put a colon, and then what I want it to appear as inside of the container would be another option. We'll leave it as scratch.global for now, and we'll come back and look at some other options that we have for binding configuration in a little bit. But for now, we can add this one bind scratch.global, and we say Rocky Linux h.sif. And now back inside of the container context, if I ls-f on the root of the file system, where before we didn't have scratch.global, now we do. And I can ls scratch.global, and we can look at all of the not especially exciting things that I have going on inside of my particular directory here, or any subdirectory that you have access to should also be visible to you, because it binds the directory and then all of the subdirectories that are its contents as well. Like I say, we'll look a little bit more in depth on binding and some different options you have there in a little bit. Then the other thing that we can do to sort of run something inside of a container, aside from the shell command, is to use the exec command. Whereas a shell starts an interactive shell that you have to affirmatively exit from, the exec command will allow you to specify an image, a command to run in that image, and then once you run that command and the specified command completes, it will immediately exit. So we can say apptainer exec Rocky Linux 8.sif, and I say ls-f/. So it is exec, the name of the image, and then the command that we want to run. And this runs immediately, gives us, because we didn't bind anything this time, the same result as we originally had, and then drops us back into the host file system. And there are ways to customize exec with bind and with other similar properties that we will look at as we continue. Now, it's also possible for both the shell and the exec to, instead of specifying an image file, you can specify a URI at a remote repository. So for instance, if we wanted to, we could say exec docker // project /root. So here's one where we have the project name, then the name of our particular software. And then we could run the command root -b inside of that. And what this will do is all in one step. This will download the image to your image cache, run the command, and then exit. I don't usually do things this way because I prefer to have a file that exists locally for this that I control of a particular version stored in a particular location. And this also, like if I run it right now, depending on how responsive the server is, my running a root-b command is going to depend on the responsiveness of the remote repository to actually download those things, and it's also going to depend on the complexity of converting that to an app container format, which that conversion should be cached as well, but if there's any particular change that happens at the repository level, the conversion has to happen again. So if this is a large complex image that changes frequently, and I don't necessarily care about downloading each of those changes specifically, I'm potentially spending a lot more time waiting for this download and conversion step that I need to be. Say this one thinks it's going to take roughly half an hour. Probably won't take quite that long, but I'm not interested in waiting for it here. So I'm going to Control-C to end this. Cancel that download process. But I did want to flag that this is at least possible because for some smaller image files or for some that don't change very frequently, this can be a convenient way to access them for some workflows. I just don't happen to usually engage with those workflows myself. Right. So I had mentioned that this is downloading to an image cache, and if things change, it needs to download again. Let's more explicitly look at what that image cache is. So demonstrate what it does, I'm going to remove our Rocky Linux 8.sif image here, and then I'm going to download it again using that same pull command. Pull / library default Rocky Linux 8. And whereas the first time that we downloaded both this and our Rocky Linux, I got a little download bar as it was being physically downloaded to our system. This time we just got a little note saying use cache image, and then by ls, despite me having removed it, it is back here without having to perform a download again. And that's because if the pull command is able to, it will use the cached version of whatever image you are requesting rather than downloading it fresh in order to save on time and server strain for the folks who are providing these repositories. We can take a look at what is inside our cache if we say cache list. And we get a sense for the number of files that are in there and the amount of space that is being taken up. Right now, I don't have very much because I just cleaned this out recently. But if you're working with either a lot of containers or with large containers, especially right now, containers that bundle NVIDIA drivers for CUDA and AI type workflows, you can very quickly build up a large cache that can become tens or hundreds of gigabytes in size without really feeling like you're doing too awfully much to get there. You can get a little bit more information about what's in here if we add the -v flag to our apptainer cache list command for verbose. And this will enumerate the different entities that are present in here. They're not labeled in an especially helpful way in a lot of cases. This is some checksum hash that uniquely identifies the particular item. But we do get a date when it was created, the size of that particular entity, and the type of item that it is. The type gives us sort of the first bit of information about what we're looking at here. And blob, the one that we have the most of here, these are types of files that come from Docker and Docker compatible repositories that you can think of as each being like a layer of a final image, where they might contain certain information that is part of the final image definition, but they are not by themselves fully useful. You need a collection of blobs in order to compose a useful image in most cases. And so we have all of those individual blobs cached locally from when we were pulling from Docker Hub a couple of times. Then those are combined for our ingestion into this other type, OCI-TMP, which is sort of the final composition of those blobs into something that is directly apptainer readable. This is like a CIF file. It may actually be named CIF on disk, but it is at least in the CIF format. Is that composition of blobs. And then library here is the type indicator that we'll have for things that we directly download from a Singularity or apptainer compatible repository. So this is directly pulling a CIF file from somewhere else where it existed as a CIF file, and we're just downloading a copy of it. Whereas with our blob and OCI temp, we're downloading a collection of blobs and then locally converting them to a CIF file, which is our OCI temp type here. And like I say, if you're working with a lot of images or you're making a lot of changes to an image that you're repeatedly rebuilding, you can get the number and total size taken up by your apptainer cache to be quite large, potentially much larger than you'd like to have in your home directory on a regular basis. The first thing that one might do to address that would be to clean out your cache. So we can say apptainer cache clean as our new subcommand. And we could run that and it will say what it's about to do, delete everything from your cache, all containers from sources and all of our blobs. And I don't want to do that right now, so I'm going to hit no, because I want to explore a couple of these. But this would be the command to run if you just want to wipe everything out. If you want to only wipe out a certain type of thing, you can say apptainer cache clean -T. So I'd like to get rid of only things of type blob, because maybe I'm okay not having these around, but I do want to keep around my final sort of useful images. And then we'll get the same confirmation about what would be going on, and it's notifying of the dry run option if we wanted to actually run this and see what would happen. But I'm going to say that I prefer not to run that right now as well. And you can look at the apptainer cache command to get some more information about additional customization you can do with clean if you need to get more creative about the subset of stuff that you're getting rid of. Now, it's also useful to know where this lives on disk. So by default, we are in our home directory for our cache, directory named .apptainer. So a hidden directory named .apptainer. And then we are in a subdirectory there named cache. We have different subdirectories based on the different types of things that we're looking at here. A couple more types than are represented in our list currently. Currently are cacheable. And we could say then library, and then this is the entity from our list here, named, excuse me, with that same SHA sum that we see in our list here. Uh, Now, if we're curious about what that is, we could say apptainer inspect as a new subcommand, pointing to this file now that we know where to look for these cached files. And this gives us a little bit of information about what it is. We bootstrapped it from Docker, from a Rocky Linux 8.6 definition file. Or rather, we didn't in this case. That was done prior to it being uploaded to the Scilabs repository using this Singularity version 3.10. So depending on which of these you're inspecting, you can get just a little bit more information about what exactly it is. You can, if you want to avoid needing to clean things out in your cache for a particular set of container operations, like you're downloading something that you know you're never going to use again, so don't bother caching it, and we can say that in advance. We have access to the disable cache option here, where we're say going to apptainer pull dash dash disable cache, and then we would give the URI. So I'll say, just for the sake of example, pointing to Rocky Linux 8 again. And if I were to run this, this would download that Rocky Linux 8.sif again from our default Scilabs library. And it would not interact with the cache in two ways. One, it would not save anything to the cache if it did not already exist there, so it wouldn't take up any additional space. And disable cache also means that it's not going to read from the cache in order to generate the result of this. It's going to download it fresh. So this forces you to interact directly with that remote library rather than whatever you might have cached locally, either to save on disk space or because you want to insist on, no, don't use anything that I have in my cache, get the latest one specifically from that repository. We don't need to do that. There are also environment variables that you can change and set in your bash RC to change the location of the apptainer cache if you are so inclined. Do not have the current of these assembled into these notes here. So let me just pull this from my other tutorial really quickly. It's conveniently named. So if you were to export a new value for this apptainer underscore caster variable that I've pasted in chat there, I don't want to interact with it here in the terminal, then you could choose a different location aside from that .apptainer/cache directory. For instance, you could use a project directory if you need to have your cache stick around longer and be of a larger size. Or you could use the global scratch if you needed a larger size but didn't care if it stuck around. You could also use a local /temp location for a particular job. if you don't care how long the cache exists for after you're done using it for these first few commands, but you want maybe faster performance on writing to it and reading from it. Maybe some examples of customizing the location of the cache that might be convenient for working with these containers. What questions do folks have so far before we move on to building containers? That's not updating. Since when have they not been updating? If I say clear, are you saying a clear terminal now, or has it stopped?
Um, no, I'm not seeing anything.
Stop share and reshare. See if that does anything for us.
It was after you pulled the Rocky Linux image, not the first time.
By ls, are we seeing updated?
I can see that. Yeah.
Okay.
I guess when you were talking about environment variables and stuff like that, I wasn't seeing anything.
Well, I didn't put the environment variable in the
Oh,
in
okay.
here. I pasted the environment variable into chat, just so
Gotcha.
I
Okay.
don't want to interact with it here. But it sounds like other folks are able to see this, and you're able to see things updating now. So I think we're
Yeah.
good to go.
Yep.
Excellent. Yeah, thanks for checking on that. This would be not so useful if you can't see what's going on. Perfect. So then let us request ourselves some jobs here to build containers within. This is the best practice for building new image files. Is to do it inside of a job because you might run out of temporary disk space or memory if you're running on one of the login nodes. So I'm going to give myself 6 hours with the salloc command, just so it definitely runs through the end of our workshop here. All I need one node. Tasks per node. Give myself a 4. Uh, and this can run on either the MSI small or MSI large partition. And I can give myself 48 gigabytes of temp space. That's the local SSD that lives at /temp, which we'll be using heavily for this. And then dash dash mem equals 16 gigabytes. This will be plenty of space and memory for our examples today. When I'm doing this for my own container work, I'm more frequently getting 64 and 32 for these, but we're not going to need quite that much today. There's a question in chat about why I don't use srun for this, and that's just a preference that I have overall with engaging with interactive jobs. Srun would drop me into a shell directly for that job that I could interact with, and then as soon as I exit that shell, the job ends, whereas salloc requests a node or resources on one or more nodes that will continue existing that I can start a bunch of sessions in. So in a moment here, we'll get the particular node that's been assigned to me, and then I can SSH to that. And that gives me the freedom, like if I mess up my shell session somehow, I can exit that shell session and then SSH back in to get a fresh shell on the same consistent job. It also allows me to have a persistent temp directory if that's of benefit to my workflow. But you are perfectly welcome to use srun for building image files if you prefer to do so. This is just a workflow peculiarity that I have. Then I will be connecting to that ACN 150 here. Or I get a stern warning that I should disconnect if I don't meet these criteria. And then I'm on the new host. I'm just for workshop space, I'm going to set my PS1 so it doesn't take up half of my terminal here. You don't have to change your PS1 if you don't want to. I'm just giving myself some more screen space to work with. So, and because we're not asking for a lot of resources here, and we're pretty flexible about where we can get them from, the job starts relatively quickly, even for groups like MSI staff that are fairly high in terms of their usage. So hopefully everyone is able to connect to a job via salloc or srun or your preferred method fairly shortly here. And clear to get myself some space back here. And then I'm going to CD into temp, which is that 48 gigabytes of local SSD space that I requested. Where there's this is emptied out at the end of each job, so there's nothing in here aside from this sort of structural lost and found directory whenever we start a new job. And then I will modularly load Apptainer so that I have that available. And I am moving into temp because, as I mentioned previously, it is a more responsive storage solution than the primary storage that we have for a user or group directory. That's because temp is SSD that is directly connected inside the node hardware, so like on the same motherboard. Whereas the user and project directories are accessible over a network. And so there's that extra hop that can add delay, especially when we're modifying a large number of files, as we sometimes need to when we're working with containers. So being inside temp as our working directory here will let things run substantially more quickly than they might otherwise, at least on an average day. So yes, let's build ourselves our first container. And let's first do it sort of interactively using a concept known as a sandbox. So instead of directly creating that .cif file, as we did with the pull command, we're going to download effectively the contents of a CIF file into a directory that we can interact with just like any other directory or nested set of directories on the file system. And then we can use Apptainer to interact with that to modify it as sort of a pseudo container before finally converting it into our final format. So to build a container, we use the build subcommand. And then to build a sandbox, we use the -- sandbox flag, where for a sandbox, we need to specify the name of the directory that we want to populate. We'll call it my Ubuntu. And then we'll grab from Docker Hub this docker://Ubuntu 24.04, which is their latest long-term support release. So we'll see this version come up a few times here. Go ahead and run that. It's going to download and build that very quickly because it's not a particularly large image. And if I ls, I see that I now have this my Ubuntu directory here. And if I ls the contents of it, I see, oh, that looks an awful lot like the root of a file system. And indeed, this is sort of that CIF file expanded into a directory, and we are looking at the root of what that CIF file would be. And we could poke around in here using commands on the host to change things if we wanted to. I don't really want to right now. I want to use Apptainer to modify the contents of this. So I will say container shell, and then I'm going to use a couple of new flags here. I want to insist that the image that I'm working with is writable because I want to modify it. And then I want to also use an option called fake root, which allows me to pretend to be the administrator inside of the container context so that we can, say, install software using the bundled Ubuntu apt package manager. And then we specify the name of the directory that we want to run our shell in here. And if I run ID now, I am indeed successfully pretending to be root. This does not give us any special privileges outside of the container, so this will not fulfill your hacking needs, unfortunately, on MSI systems. You have complete control over everything inside of this directory that you own. Good, but outside of that, you are still just your user. And now we're in this Ubuntu environment. I can say, all right, whatever default Ubuntu was downloaded from Docker Hub maybe didn't have the tools I need. So I can say apt update, where apt is the package manager that comes with Ubuntu. This will download the latest package lists for the app repositories. And then I can say apt install. I know that I want to get build essential and wget for the example that I'm going to be using here. An apt has its own full rich interface that you can use to search for things that are available and install particular versions and particular sets of things. I'm just going to grab whatever it gives me for build essential and wget because I'm going to be, in our example here, building some code from source that I need to download using wget. It's going to list all the changes that it's going to make inside of our sandbox image here, where it's going to download a bunch of new packages, taking up about 350 megabytes of space. And I'll say that's fine. And it's going to go ahead and execute that for me here. And this is one of the steps where we're gaining some speed by running on /temp because it's interacting with a lot of files to get this operation set up. And then it's done. So we have installed our build essential package and also wget. So we can use those inside of our image here to build. The example we're going to be doing today is Hammer. This is the same example that we used in the Apptainer sort of preview in the software management workshop a couple weeks back, but we're going to be looking at it from a couple different angles today. So first, we will create ourselves a directory where we are going to download the Hammer source code and install Hammer from. And these will be directories inside the image, the sandbox image. So inside of opt, we're going to make a new directory called Hammer, and we're selecting opt as our location sort of by tradition. This is because we're root in here, we could select any of the directories inside of the sandbox to install our software, but opt is where we put optional add-on software packages for a particular running Linux operating system. And it's where a lot of container developers have agreed to put software they're installing from source inside of a container. And so we choose to obey that convention here. And so we're going to make our Hammer directory inside opt. We'll cd into that. We can download our source code. And we will get http edulab.org/software/hammer/hammer.tar tar.gz, which will grab us our source code here. I just got signed out of my notes. Some timer has just gone off that signed me out of my notes, which is not very convenient. So let me re-authenticate that. Apologies, two-factor authentication is taking a moment. Alrighty, so we've got this available to us. ls, we have hammer.tar.gz. And we're going to expand this using a tar command, tar-zxf, to inflate hammer into a directory that we can work with. I'm going to, so there's a parallel here between what we're doing interactively and what we're going to do with a build script later. I'm going to do an additional step that is not strictly necessary here, but will help us later. Where I create a symlink from this hammer, whatever the directory version happens to be, to a linked directory named source. Excuse me. Then we will cd into source. And we see we've got our configure script here. So we can /configure -- prefix equal /opt /hammer /install. So we're going to, inside this hammer directory, have a location where it's installed, as opposed to it being the source code here. So install lives right next to source. We'll run this, and this is the part where all those build essential tools that we installed are being used. Then we'll make, actually compile the code, and then we'll make install, and this is done to install it into the final location. And I'm sort of breezing over the install logic for Hammer itself here. It's available on the Hammer website if you are curious reading more. There's also documentation included with the source code if you want to look at what the developers have to say about building it. But we're here just interested in demonstrating that we can build and install it inside of a container as our example. All right, that's all done, and we can make install. All right, then if we opt hammer, we have our source code, we have that source link, we have the original tarball. If we look inside of install, we have the directories, one of which contains our executables. So we've installed software inside of this this particular sandbox image. We can exit, and we can use the apptainer exec command to run software that we just installed. So we can say apptainer exec. We give the name of the sandbox that we want to run out of, and then we give the command opt hammer install bin and hammer -h is what we'll run. So get the help for nhammer, and we can see this command produces the expected output, the help information for the nhammer tool. ls my Ubuntu for completeness. If we look in opt hammer, we can see from outside that we have in fact modified the sandbox as well. And by running the sandbox as an image file like we just did, we treat this directory as the root directory, and so we refer to the path from the slash opt hammer install bin. And we can also open a shell in this if we want. The apptainer shell, my Ubuntu, and then we can, if we're going to be working in a shell in here for a while, we can say export path equals previous value of path opt hammer install bin, so that we don't have to type out the full location of the executables with each of them. And then we can simply type nhammer -h or phammer -h or whichever of the tools that you like, because we've now included that bin directory where they've been installed on the path. Now that's not super convenient, and there are some conceptual drawbacks to using a sandbox like this as well. But if you are trying to troubleshoot and figure out how to get a particular set of software up and running, and you need to sort of fiddle around with things in order to understand what's going on, using a sandbox can be convenient for that. It is possible to then take the sandbox that you've built and convert it to a CIF file, so that you can just have this one file to pass around to other folks, to upload to a repository, et cetera, et cetera. But it's not the way that I would recommend creating a CIF file. And we'll look at my recommended way in just a moment here, which is to use a definition file, which will give us a number of benefits over the sandbox approach. Primarily, that one, we could just give someone else the definition file if we want them to be able to use our software. And that will be, a couple dozen lines of text instead of potentially a couple dozen gigabytes of drivers. So you could post it on GitHub and just give someone a link, or even email a definition file if you're so inclined. They're also very amenable to version control, which is nice. And they also leave a record of what you did to create the container. Because if we were to convert the sandbox that we just generated here into a CIF file, we would not know anything about that CIF file, except that we made it out of this sandbox. We wouldn't have any history before that about the app packages that we installed, about how we built Hammer, about any other customizations that we may have made. And we're also limited on the types of customizations we can make. For instance, it's not very convenient to modify path and build that into a sandbox that is then turned into an image file, whereas a definition file provides a nice way for us to do that. And we will look at definition files in a moment, but we are at a time that seems good for a short break, so that we can rehydrate, recaffeinate, stretch our legs before continuing with the rest of the material. So we'll be back, let's say 10 minutes before we continue with definition files. And I'll see folks once we're all back from that. Alrighty, that's our 10 minutes for break. Welcome back, everyone. And let's go ahead and move into building images using definition files. It's clear. Um, and let's go ahead and create ourselves a new text file. We're still inside the temp directory here. And so we're going to open a new text file, call it hello world.def, as is standard for a lot of these first attempts. And feel free to use your own text editor of choice. I'm just most comfortable with VI. So in here, we're going to provide some information to specify the image that we want to build and some behavior for how we want it to run as a container. So minimally, this will look like a bootstrap entry where we are going, this is essentially replacing the URI on the pull command. We're saying I want to grab from Docker, and then from Docker, I want to grab Ubuntu colon 24.04. So these two lines together replace the Docker colon / Ubuntu colon 24.04 and say we want to use that same Docker Hub image to build our container, or rather our image file as specified by this definition. We could just leave it at that if we wanted to and say, I just want to grab exactly that. And it would be a very interesting file. So let's give it some behavior in the form of a run script. And we'll see a couple of these different section headers for definition files that start with a %. Run script is the one of these sections that allows us to define a default behavior for containers run from this image. And for our hello world, I think we can echo hello world with some enthusiasm. And inside these definition files, we are allowed to use the hashtag or # or octothorpe, depending on your age and first exposure to this character, to indicate comments for later readability. So I can say print just to redundantly describe what's going on to demonstrate the comment syntax here. Then for our minimal hello world, this is all I need is something to bootstrap from, and then some default behavior. So I can go ahead and save and quit this. Once more. Then I can say apptainer build, and then the build subcommand takes arguments in sort of a strange order for me, where we first specify the thing that is being built. So we are building something called hello world.sif, and we are building it from our file we just made called hello world.def. So the final image file is our first argument, and then the next argument is the definition file that we're working from. Go ahead and run that. It doesn't take much longer than just downloading the image and converting it over. And so we have this hello world.sif. Now, we haven't taken advantage of this yet, but you may have noticed that all of the SIF files that we have interacted with so far, and this will be true of our two Rocky Linux examples as well, they are executables indicated in how I have my ls customized with this asterisk. which means that we can run our images as a program if we are so inclined. And what we just defined using that run scripts section in the definition file is what happens when we run this as its own executable. That's what I mean by the default behavior. We can get that same outcome if we say apptainer run hello world.sif is equivalent to running the image as an executable. So it can be handy to define a default behavior if you're building a single purpose or a one very most common purpose image, so that you don't have to deal with the exec functionality and can simply run it as a program that does the thing that you have put inside of the image and containerized. We're still allowed to apptainer exec if we want to. We could have it echo something else instead, and we bypass that default behavior if we use exec. So it doesn't limit us in terms of what we do if we define that run script section, but it does provide this bonus default for us to use. Then if I want to, having built this container, I decide, no, I don't want this anymore. In order to put a little brain fart there, I can just remove hello world.sif and the image no longer exists. I'm free to rebuild it from that .def file if I would like, but there's no finicky uninstallation procedure that we have to follow. We can just delete the file or move it somewhere else, or because we're in temp, I could just end the job and it gets automatically deleted as well. So that's sort of the type of entities that we're interacting with here. So this is maybe not a very interesting example, our hello world.def. So let's go back and create a definition file that will adapt our hammer build that we did in our Ubuntu sandbox into a definition file format and add some convenience and some extra information that will be a little friendlier to work with. So I'm going to open a new text file. Okay. I can type, I promise. So hammer in ubuntu.def, the name of this thing. And it's going to start off the same way because we're happy in this case to bootstrap from Ubuntu 24.04 again. And then we're going to introduce a few new sections here. The first one, which is going to contain the meat of what we are doing, is a section called post. And the post block here is going to be a set of commands that are run inside of the container environment as part of creating the image file that we are defining here. So these are run once at creation time when we are building the image, and then never again. And so this is where we're going to put all of our information on how to download and build Hammer. And we don't need to be indented here. I just like to be for easy readability. Need to apt update to apt install build essential wget, and then we need an additional flag here on apt install, because if you recall, when we did this interactively, it asked us, after enumerating all of the changes that were about to be made, would you like to proceed, yes or no? When we use a definition file like this, we don't get the option to say yes or no interactively. The script is just run, and if it hits a point where it waits, then it will either, depending on the particular tool, wait indefinitely or recognize that it cannot proceed and then quit. So if we want to auto confirm with apt, we say -y to make sure that we accept those changes and proceed with the installation. Then we're going to make that hammer directory under opt, and then we're going to cd into it. And then once we're in there, we will wget edulab.org/hammer/software/hammer.har.exe. Then we will our cxf hammer.har.gz. And then this is where that symlink is going to be helpful for us in this particular case. You'll note that Edulab does not indicate a version of Hammer when we are downloading from them in this way. So they could change the version that we're downloading in the future. That's what is contained in this hammer.tar.gz. It happens to be 3.4 right now, but it could be 3.4.1 or 3.5 at some point in the future. So that this build script is future-proof, whatever that version is after we inflated its hammer dash something, we're going to link that hammer dash something to a directory named source, and then we will cd into source in order to continue with building our software. This is just kind of future-proofing against different hammer versions that might exist at the same URL. And once we're in there, we can configure setting that same prefix and install, make install. And this is all we did really interactively to install Hammer, but we can get fancier inside of our definition file to make things a little bit nicer when we're using the resulting image. To do that, we'll build ourselves another section, environment, and this is a set of environment variable modifications that are applied every time the container is run, except for when running post. So post runs to create the image file, and these environment modifications are not present at that time. So any environment modifications you need in order to build from source correctly, or for convenience, you have to set in here as if this were a bash script. This is the runtime environment variables. And the one that we're the most interested in for our Hammer install here is adding the location of the Hammer executables in opt hammer install bin to path, so we don't have to include the absolute path of them when we run them in later usage of this this image file. And we could make additional modifications to the environment here if we wanted to. This is a block that can be as big as you like. We only need the one for our particular case here. We may as well include a run script, which we can have as just for fun, printing the Hammer help output here. Not very useful, but it'll demonstrate that this does have some default behavior. Then we can add some labels in a new section, helpfully labeled label. And this information would appear if we used apptainer inspect on the resulting image file. So I can say the author of this is me, and I can say the version is v0.0.1, or whatever version I choose, and I can include additional information to my taste here that would show up when someone inspects the image to get a sense of what's going on. And we can also add a help section that might include examples on how to use this image file correctly. Maybe declaring like what the default behavior is actually doing, um, guidance on when or when not to use this, whatever you want to have in a help section. I'm just going to have a little descriptive thing here saying example container running the and help documentation. It's not a very helpful help because it's already doing that in the run script, but just to demonstrate that that help is available. And then this is all I want to do. So I'm going to write and quit. Yeah. Mistakes, but I guess we'll see in a moment. Then building this will be build error in Ubuntu.sif. We're building this image file from hammer in Ubuntu.def. Again, that's sort of inverted syntax from what at least I expect. And if we run this, it's going to grab that image and it's going to run all of those commands to install the dependencies for Hammer. It's installing stuff via apt right now. Then grab the Hammer source code, compile it, install it to the final location, and then it will spit out an image file that we can use in order to use the Hammer software if we are so inclined. And this shouldn't take too awfully long because we are running it out of /temp. Looks like we're getting close to the end here. There we go. And it's very bad at estimating how long things will take. But we'll, in a moment here, have our image file to interact with. All right, we have hammer in Ubuntu.sif, which we can run as we defined as an executable to get that nhammer help. We can add exec hammer in Ubuntu.sif, say vhammer -h. We are on a different command to grab that other executable. We can use the aptainer inspect command to see some of our tagging information here with the author and version that we include, plus some additional information that was already tagged for the underlying image. We can say aptainer run-help for this image to get the help blurb that we included in there. And we can even get back the definition file. We can say aptainer inspect -d, I believe, is hammered in.sif. And the image file can report back the exact file that was used to build it, which for me, this is the killer application of building from a definition file, is the resulting image has a built-in record of how it was built, which is just very useful for looking back on collections of these images and saying, oh, which one was this exactly? I lost track. Oh, I built things exactly this way and for this reason, and here we go. Um, and we still also have independently this hammer and Ubuntu.def file that we can put in version control or email to someone trivially if we want to have them recreate our environment without necessarily needing to send them a potentially large CIF file, depending on what is contained. Let's see. And so I guess the summary of why I prefer and would recommend using definition files rather than a sandbox and then converting that into an image is it avoids creating a black box container where like you might make it correctly and it might work and do what it needs to do, but with that sandbox created image, there's no record of how it was made. And so if you need to recreate it or create a modified version of it, you're potentially out of luck without a lot of trial and error to fix it. Whereas if you build from a definition file, then you get this nice self-documenting behavior that you can use to your advantage a few years down the line. So be kind to your future self and use definition files when building these things where possible. And I will also comment a couple of other pieces of advice here that we haven't explicitly touched on. So it's, as I mentioned, best practice when we're installing software from source like this to target /opt. This is because it doesn't step on any of the operating system directories, like /bin or /user bin. You run less risk of creating conflicts that will end you up with a non-functional container environment. And you don't want to install into /home or /temp from the container because, as we'll see shortly, those are mapped from the host into the container by default. And so you're not actually installing into the container if you're installing into those locations. And you also want to note that this is not sort of secure or encrypted in any way. Anyone who has their hands on this image file and can run it is able to access the contents. So make sure that you're not including sensitive information like passwords or cryptographic keys or sorts of things that you wouldn't want to be freely read by anyone who has access to your image. It's a common issue that you hear about in the enterprise world that someone has baked in a secret into a container and caused a security gap. So I just make that visible to you all as you're getting started working with containers, so you can choose to avoid that and not cause security issues for yourself. What questions do folks have about using definition files? All right. Hearing none, I guess everything was clear. Excellent. Then let's go ahead and proceed and look a little more in depth on how we bind directories from the host into the container. You will recall the app container shell -- bind scratch.global. And then we specify an image file we want to use. We can allow scratch.global to be visible and accessible inside the container context where it would not otherwise be unless we include this bind. So we're going to explore a little bit more about the binding behavior here. So first, as I mentioned a moment ago, there are some bind paths that are automatically included by default. Oh, and we do have a question about build files. So the question is, how deep do we have to go in the software install? Do we need to start from a Linux version? You do need to bootstrap from something in principle. So you can actually bootstrap from something that is less featureful than a Linux version. You can bootstrap from like a wget or a curl if you just need to download stuff. But the most frequent workflows are to either bootstrap from a Linux version, or you might bootstrap if you're doing a GPU-driven workflow. You might bootstrap from an NVIDIA-provided image file that has all of the NVIDIA drivers and functionality already set up, and we'll discuss the couple of special caveats there for accessing those. Then you install on top of that slightly customized Linux distribution. But yeah, most commonly you're installing from a Linux version or a customized Linux version that will add some niceties on top. You can, of course, in principle, also download a finished image file that has the software you want if it exists. But then you're not necessarily building unless you're customizing on top of that. And it sort of depends on what's available from the different repositories and what's closest to your desired endpoint. You're welcome. So bind paths that are included by default. So the things that are automatically passed from the host context into the container are whatever the home directory as defined by the home environment variable is, whatever the current working directory as defined by pwd is when you run the shell command or exec command, whatever the working directory is where you run that is passed in to the container context. And there are some system-defined paths like /temp, /proc, and /dev, I believe, are the relevant ones at MSI that are passed in automatically as well, that enable the running container to coordinate resources with the host operating system a little more effectively. So that's why, for instance, you don't want to target installing things into temp, because that actually targets the host temp, not the container temp. And you very rarely want to install software into a directory that goes away at the end of your job, except when we're doing workshops, like we're installing everything in here now. Now, if for some reason you don't want any information passed in, we are able to exclude either particular paths or all paths. We say, oops, I see a typo there. So for instance, if we did not want temp to be inside of Hammer and Ubuntu when we ran it, we could say container run dash dash no mount. And then we said we don't want to mount temp into hammer in Ubuntu. So, and it doesn't change the behavior here because we're just running an executable for this particular case. And we can specify other things not to mount either as a comma separated list. If we also didn't want to mount home, we could say no mount temp home, or we could just say home if we don't want to mount our home directory, which again is not going to impact the behavior of our hammer of Ubuntu here. If I make this a shell instead, container shell, we're not mounting home in this. If I ls 3.0404, I get an error that I can't access that because I specified don't mount my home directory. Whereas if I get rid of that no mount, just to demonstrate, the behavior before specifying no mount. So I can explicitly block out the inclusion of my home directory if that's desirable for a particular workflow. It usually isn't for me, but know that option is available. And if you don't want anything bound in, like this is a fully self-contained situation, you can say dash dash no mount, and then you say bind paths. And any bind paths that are set by default will no longer be included, and all we get is the bundled environment here. Which is not something that I'm frequently in need of, but again, just flagging that it's available if you do. But we don't need to run that here. So just for emphasis, let's look at binding some a directory that contains some fictitious data into our hammer in Ubuntu image file here. So we'll go ahead and make a directory called my data, and we'll echo UMS is 105.6 mega electron volts, and then we'll redirect that into my data. We'll call that muon mass.txt. And then I can say shell dash dash bind, say home, my data, and then I'll customize the mount location. So it won't be under home my data. I want this to live at the root of the container, say, to customize for my convenience under /data, because I'm going to always be, or very frequently be referencing muon mass in my workflows in here. And I don't want to have to type out all of this. So we'll just type out a shorter data path. And then we'll then ls/data, which contains our muon mass .txt from the root level, which can be very handy, again, for typing convenience and clarity. If you have something that's useful to bind in that's nested in very many particularly named directories, and you just want to have a convenient location inside of your image. Now, we can bind multiple paths using the same format. If we have a comma separated list here, I can say scratch.global. And I don't have to include that colon for each of these. I can either choose for each of these comma separated values to have a colon to customize the location where we bind inside of the container, or I can allow it to bind at the same location, which seems appropriate for scratch.global. Uh, slash, I have my data and I have scratch.global, and I can add as many as I like in this way. Now, if there are locations that you either very commonly need with your containers or you know you always need with your containers, and you don't want to have to specify them all via a long and unpleasant to type bind command that has many comma separated values and is prone to typos, you can use an environment variable called apptainer bind. So if we export bind, my goodness, I type it. This will be a string that takes the same syntax as our bind argument here. So we'll say all my data binds to slash data, comma, scratch dot global. And now if I apptainer shell hammer in Ubuntu .sif without providing an explicit bind argument, if I ls slash, I have scratch.global and data already bound in there for me because I've defined this in the environment. And if this is something that you use a lot, you can have this in your bash RC or some other file that you choose to source when you are getting started with your particular work. Now, I will say that we use the apptainer bind variable in some of our apptainer driven modules. So the I would say take care when you are setting this if you are using any module. Anything that exists under software module files bundle is an apptainer that is hidden behind a module file for convenience. And so just be careful about the value that you set for apptainer bind when you are using modules out of this directory. It won't always cause them to break, but sometimes it will. So just be aware that this interacts both with when you're running things directly as container instances and also when they're running in the background using some other tool. I believe that's all I want to say about the specifics of directories. Then a couple of specifics around running Slurm jobs that use apptainers. The most basic utilization pattern here, I think, will be fairly obvious from what we've been doing so far, but we'll just demonstrate it here for completeness, and then some slight variations on this will follow for particular workflows. So call this basic job.sh, and this will be a Slurm script like any other with your sbatch directives with the appropriate sbatch syntax. Set wall time, processors, memory, amount of temporary disk space, whatever you need for resources. Then you'll module load apptainer, and you can apptainer exec. Let's say that we're running something on one of those Rocky Linux images in my home directory that I have, and we'll say echo file. Uh, and you compose the exec command here just like you would for any of our previous examples, including your use of bind or writable or fake root. If you're working with a sandbox inside of a job, syntax remains the same in your script here. So fairly straightforward. Request your resources as usual, load the Apptainer module, then use Apptainer to do whatever you like. The one caveat would be the Apptainer shell subcommand does not play nicely in here. So that's designed for interactive use, and this is a batch script like this is fundamentally not interactive. So I would prefer using exec over shell in this context where possible. But otherwise, everything is a fairly straightforward application. Um, then things can get a little finickier if we're talking about using GPU resources for running our containerized workflows. So we'll say, let's make ourselves a CUDA job.sh. And this will look, in terms of our SBatch directives, the same as any other GPU job. Got some memory and some temp. Say that we want the partition is say MSI GPU for this. SBatch. This generalized resources or GRES. This GPU on a 100. We'll say we only need one for our particular application here, but you can change the type and number of GPUs per normal. And then we will module load container. And when we are using a CUDA-enabled workflow, we're frequently going to be pulling from the NVIDIA catalog here. So let me pause, and I'll drop a link to that in chat for everyone, the catalog of NVIDIA containers. I'll actually back out of this job file. Modification up there, and I can say container pull. Let's say that I want to grab from that catalog a CUDA-enabled GROMACS image so that I can run molecular dynamic simulation that is GPU accelerated. This will be cr.io/hpc/GROMACS colon 3.2. And I happen to know from exploring this repository that this is CUDA-enabled GROMACS, and so that's why we're grabbing it here. So it'll take just a moment to download a couple of layers, and then compile this into the final image. This one should be a little bit larger than what we've been seeing because it does include these additional drivers as part of it. No, it's not that much bigger. The CUDA-enabled GROMAX we have is 335 megabytes, whereas Hammer Ubuntu is 230. So a relatively modest NVIDIA image as they go. I'm going to go ahead and move that to my home directory because if I'm thinking about using this in a job, I can't leave it in temp here because this temp doesn't exist inside whichever other job's temp. So I have to put the file someplace where it will continue to exist. Then I can pop back into CUDA job and then apptainer exec. And then we need an additional flag here to say that I want to use GPU resources, which is dash dash NV for dash dash NVIDIA. And this will be GROMAX 2023.2.cif. And let's say that I wanted to GPU enabled print the MD-RON help menu. Not the best application of it, but we have the syntax for here. So the only addition here is one, make sure you sourced a GPU enabled container that can actually utilize the resources if you're going to bother with trying to use them inside of your job here. And then also include this dash dash NV flag so that the context inside of the container is aware of the allocated GPU resources of the job. And this is a nice little shortcut thing that takes care of passing along the specific environment variables and making sure that certain directories and drivers are present. You don't have to worry about doing those things manually. But relatively straightforward way to use GPU resources if you have a GPU-enabled container. One caveat, sometimes, especially older NVIDIA images, can be a little finicky about which devices you grab. If there are if there's any ambiguity, like we can request more than one GPU here, up to 4 on some of the 4-way nodes, as an example. And sometimes these older images will only pick up the first GPU, or if you have only one GPU, they'll be looking for like a different index of a GPU, and they have to be sort of gently redirected into acknowledging what is present. And so the way to do that is to set this environment variable apptainer CUDA visible devices as part of running the apptainer command. And this will sort of more forcibly map one or more host indexed GPUs. So we could say, if I wanted to put all 4 of them in there, I'd say comma 1, comma 2, comma 3. So GPUs at index 0, 1, 2, 3 on this host would be mapped sort of more forcibly inside of the container. Or if I only had one of those, this would simply be equals 0 to get the 0th index there. This is usually redundant. We usually don't have to do this, but again, for some older images from this repository, sometimes it is required to be a little more explicit and specific, and this is the first thing that I would try if you run into some issue with one of these NVIDIA containers complaining about not being able to find a GPU that you know exists in the context of the job. But again, usually this is not required. So I have in the material here, and we're not going to cover it fully in our interactive workshop here for the sake of time, but I have an example of sort of step-by-step how to run MPI parallel codes using apptainer. And there's a worked example for getting a little MPI test application containerized for use. And so you can follow that through and read the material there if that is something that is of interest to you. Um, the the basic takeaway for this is when you are building your container, you want to include inside of it an MPI runtime that is the same as an MPI runtime that exists outside of the container. So for instance, we could, looking at the open MPI things we have available, we could say, I want to have a container that internally uses this 5.0.8 version of OpenMPI. And the code that's built inside of the container also uses that as part of its build toolchain. Then at runtime, we use this external module outside of the container to essentially MPI run and then instantiate the apptainer command as a subcommand of MPI run rather than flipping it the other way. And there are some implementation specific reasons for this that make this a little finicky. But the gist is if you want to be able to run across multiple nodes in a Slurm job, then having an external MPI that matches the MPI inside the container is going to be the most straightforward way to do that. And that's what the example takes you through. But it takes a fair amount of time to type out and build. So we'll omit it for time here. Then one final topic that we have is another way to run software using these image files. We've seen we can have an interactive shell. We can have a command via exec that automatically runs and exits. And we've seen that we can have a default behavior via that run script section of the def file so that you can use the image as sort of its own bundled executable without necessarily having to invoke any apptainer commands to get that behavior. An additional option that we have is to create what are known as instances of containers, where we, from an image file, create a running container that then just sort of stays running in the background. This can be useful for certain interactive workflows, similar to the way that I'm using salloc here to be able to connect multiple sessions to the same job. You can make an instance and then connect multiple shells to that instance if you're so inclined. But the killer feature, in my mind, for using these instances, you can run server type applications that need to run some daemon that waits for input. And you can use an instance to run that containerized daemon and then pass it information over some network port or however else the daemon wants to engage. And that allows you to do things like run like a web server or a Jupyter Notebook instance that is fully containerized and controlled by you. There are other software packages that use this type of workflow that can benefit from instances, but we'll stick with a small web server for our initial example in just a moment here. But first, let's look at our syntax. So we've still got our Rocky Linux 8.sif there. We can say, I want to start an instance. Syntax is apptainer instance start. So the subcommand and the thing we're doing with the subcommand. I would like this to run from the Rocky Linux 8. And then an additional argument, I would like to name this instance my Rocky 8 so that it's easier for me to know what it is when I look at the instance list. Get a little warning that instance stats will not be available, but that's not of much concern to us. Say apptainer instance list, and we can see that there is this currently running instance named myrocky8, as I specified here. It's got an ongoing process ID, and it's running from this particular image. And then I can say apptainer shell. My terminal got angry at me for a second. Apptainer shell. Then I can, instead of specifying an image file, I can say instance my Rocky 8, putting back to that name. And then I'm dropped into this already running instance. And if I had a different terminal and a different window, I could have a second terminal connected to the same instance, which this is one of the only ways that you can get sort of multiple sessions into the same container at the same time. Always can be useful for certain troubleshooting workflows. As an example. But the Rocky Linux 8 image, we haven't set it up to do anything as an instance. So all it's really doing is sitting there waiting for us to connect via a shell, which is not super interesting unless you have the specific need to connect multiple sessions. So we'll go ahead and exit this then. And then we will also stop the instance because no reason to leave a boring instance running. So we'll say apptainer instance stop Rocky 8. Stop my Rocky 8. And then if we instance list, now we no longer have that entry because that particular container has been stopped. Now, starting the instance takes a very similar syntax to exec. So for instance, if I wanted to edit this command to include bind scratch.global, I could do that. It would also respect the apptainer bind path as well. It would respect the --nv if we wanted to include that. But just to flag that this customizes in the same sort of way as the shell or the exec command would. But let's make something that actually performs as a server as an example here. So let's make ourselves a little web server that will contain a little HTML web page that we could access. So let's make ourselves index.html. So I'm not going to type HTML right now. I have a hard time with typing accurately, and I don't do HTML. So I am pasting in my HTML from the page about instances here, which I've pasted the location to the material in the chat. But just for brevity and saving myself some almost guaranteed typos, just pasted the example in, which will, if we were looking at this in a graphical browser, give us a window that was titled My Awesome Service. And then on that page would have a header that says Hello World with some body text that says, I can see this page, my awesome service is up and running. And so this would potentially be accessible via a web browser if we had web browser access to this particular node. is the idea here. Go ahead and save that. Then let's make ourselves another definition file that is going to be our basic server definition. We're setting ourselves up this little web server. We're going to do our favorite thing and bootstrap from Ubuntu. I haven't updated this example yet. I don't know for sure if it works with 24.04. I have a note for myself to check on that. We'll go back into the past, 20.04 for our bootstrap here. Then we will, using the slightly older syntax for apt from the 2020 Ubuntu release. We will update our repos and then install Python 3.9 as one potential quick, easy way to get a web server up and running. Then we'll introduce a new def file section here called files, where we're going to include this index.html file that exists in our working directory, but outside of the container. And I'm going to copy it at runtime, which is what we're specifying here, into the opt directory. So anything in the files section or def file is going to take a file from a location on the host, which can be the working directory, or this could be an absolute path or a relative directory. And that's copied in at image creation to the path that is specified here. Now, if I did nested subdirectories, for instance, op/webpage does not exist yet, but this directory would be created as part of copying the file in. But I'm happy to just leave it in opt for now. Then another new section that we're going to include here is the start script. This is the instance equivalent of a run script. So when we say apptainer instance start, this is going to be the default behavior for the image that we're defining here. And what we'd like it to do is cd into opt, so it's in the same working directory as our index file. And then it's going to just run a little Python HTTP server. And then it's going to serve our index.html on port 8850 is the way this particular syntax works. So we'll go ahead and save and quit this. We're just installing Python, copying this one file in so that it's built into the container, and then defining that we want to, by default, with an instance, serve that index file on port 8850 using our little Python web server. We want to apptainer build basic server.sif from basic server.def to create our image file. Let's see. Destination. Oh. See, this is what happens when you have your apptainer caster. So the error that I got at creation time here, data creation failed. There's a mount hook issue where trying to bind that my data directory into data caused an error. because when we have a writable container, binding doesn't work quite the same. You need to overlay instead of create a new thing. Um, and so it's caused an error here. And I didn't specify any binding in my build command. So this is coming from the apptainer bind path. So we want to unset apptainer bind path before I attempt this build again. So I get the we love live troubleshooting. It's apptainer bind, not apptainer bind path. But unset bind. Now we should no longer be trying to bind in my data, and this should work. Aha, success. All right, so that is a good point of caution for when you are modifying environment variables for binding things in. Depending on how you are building your images, it can cause errors, as we've just seen here. My personal preference is to not store the apptainer bind sort of globally so that it doesn't interfere. I'm allowed to build containers as I like, but just be aware that you can run into issues like this if you do leave that set. But having solved that and built our small image, we can apptainer instance start, and I can say no mount temp, because that temp is where our original index.html file lives. So I can say, look, I don't have anything up my sleeve. I'm not including /temp, so I'm not including this index.html file. Whatever is being served from basic server.sif is something that's included in that image file. And we'll say basic server.sif, and we'll call it my web service. And instance list rather, and it's working. Then I can use a curl command to grab from the URL localhost HTTP without any encryption, which is where we are serving this at port 8850. And when I curl from that URL, I download the HTML document that is being served here. And if we were in a graphical environment, I could navigate to this in a browser, and I would see this rendered in all of its tiny hello world glory in an actual graphical window. So this is actually acting as a server now, doing something sort of unique as an instance in this case. But we don't need to keep doing that, so apptainer instance stop web service. And now it's no longer running the back. All right. We've got 20 minutes left, which historically is not quite enough time to run. I have on the instances page here an example. If you wanted to set up your own custom Jupyter notebook container and serve it in the same way, because you're doing something that maybe requires different permissions than are available on the open on-demand Jupyter notebooks that MSI offers, or you needed to customize Jupyter notebooks in some other way. You can containerize a Jupyter notebook customized to your heart's content, and then serve it in this way and access it via a web browser inside the same job. And the example that I have there takes you down through how you would set that up for customizing a particular environment. like that, and then getting in and utilizing it. Uh, but just with the build time alone, outside of stepping through it, I don't think that is going to be possible today. But it is something that you can do if you are interested, and it's documented on in the material. So then that does bring us to the end of the material that we're able to cover today. Uh, so yeah, thanks everyone. Are there any questions about using containers at MSI in general, or anything specific about the material that we've covered today? Happy to